In this session we'll see some standard shift registers. As we know very well, there are 4 different types of shift registers. Shift registers are just can be designed by adding a set of or a group of flip-flops side by side, just simply cascading. Suppose for example we want to design a 3-bit shift register, so we have to cascade 3 flip-flops D1, D2, D3 by side, and based on the configuration, these shift registers are classified into single input single output shift register. Means it accepts single data. That data will be transferred from one flip-flop to another flip-flop. Finally output can be generated from this particular output terminal. This is the input terminal, single input single output. Next, another one is single input multi output, single input multi output, SIMO. Single input multi output means in these type of shift registers, it accepts single input and we can access the data from multiple flip-flops. Next is multi input single output. In the case of multi input single output, it takes the data from the multiple lines like this and extract the data from single output, multi input single output. Next is MIMO, multiple input multiple output. In this multiple input multiple output, in another way, is called single input serial in serial out, serial in parallel out, we can say. This is parallel in serial out. These are parallel in serial out. Another one is parallel in parallel out, means parallelly we are inserting data and parallelly we are extracting parallel out data. So these are different 4 classifications: single input single output, single input parallel out, parallel input serial output, parallel input parallel output, SISO, SIPO, PISO, PIPO. So based on this 3 configuration, so coming to here, this particular question is given in the form of SIPO, single input parallel output. How single input parallel output? You can see here. So design a circuit that increase 3-bit output. 3-bit output means under the specification it's take 3 parallel bit output. By each time a rising edge is detected, a 1-bit input. The 1-bit input. So this is 1-bit input, that is basically a single serial in, and this is parallel out. This is parallel out. So serial in parallel out specification is given in the question. So based on this, we have taken this particular diagram. As a 3-bit is mentioned here, we have chosen 3 D flip-flops. This is the D1, this is the D2, this is the D3, 3 D flip-flops. Data in, the data input is 1 bit of information here, and we are extracting parallel data from Q0, Q1, Q2, 3. At the same time, asynchronous reset signal is added here. So you take this particular signal as a reset input signal, and clock is synchronized. But reset is asynchronous here. We have taken clock as a synchronizing edge, and this each time whenever the clock edge is detected, the data will be transferred. Data will be transferred whenever the clock edge is detected. So based on this specification of this particular circuit, how to write a code for this? This is the block diagrams: clock, reset, serial in data, clock 1 single bit, reset also 1 bit, serial data also 1 bit, and output is 3 bits, just we have taken 2 down to 0. Okay, so how to write a code for this? This is the library declaration. IEEE use IEEE standard.all library declaration, and we have taken entity name as SIPO, port reset is in, and S in also, serial in also input, clock also input, and P out is the size is 3 bits, 2 down to 0, and the entity. So this is almost a description for your A bit. So coming to C bit, how to write a description for this? This is your C bit. In the C bit architecture, behavior of SIPO is just we have initialized a signal, we have generated one temporary, we have taken a signal data type to define a temporary variable called temp. We have taken a signal data type. The temporary variable also we are storing of size of 3 bits. So under signal begin block start, process, clock comma reset, this begin. If reset is high, then store this 000 in the temporary variable. Else if clock is high and the clock event occurring, if the clock event is occurring, if clock is high, then assign the data into this particular value, and again this data will be shifted to here, this data will be shifted to here. And this process, finally whatever the data we are getting at the output, that data will be given as to final output value, and this behavior. So this is particular type of VHDL code for single input parallel output design, as we mentioned in the previous question. Next, coming to this test bench develop for a single 1-bit full adder. So 1-bit full adder, a VHDL design is given. How to design a test bench for this? To test a bench, as based on this particular design, we have taken a simple 1-bit adder A, B, C carry in, and output, the size of output is mentioned here. The size of output is 2 bits here, 1 down to 0, 1 down to 0. So 1 is for sum, 1 for carry out. So that's why we have taken 1 down to 0. This is the specification for the given VHDL design. So how to develop a entity? This is the answer for a entity declaration, port declaration for input and output. This is your B bit. Coming to C bit, in the C bit we supposed to develop a test bench by considering a 10 megahertz of frequency. If you convert 10 megahertz into a time period, approximately the time period will be how much you are getting, that is 100 nanosecond. So how to write the test bench? This is the standard method to write a test bench. This is the library declaration, next your entity declaration, and next your architectural declaration. In the architectural declaration we have defined all the inputs and outputs, and next input declaration with signal data type, and next output declaration with signal data type, initialization of unit under test. This is your port declaration, and the stimulus process starts from here, and we have taken 100 nanosecond as because the question is mentioned there 110 megahertz. So at 100 nanosecond we describe all the input variables here, and architecture for test bench for 1-bit adder. Again the different signal values are given. So like this is a standard UUT method. I think some things got repeated here, so already we have seen this. Basically you can follow like this. So stimulus cases we are taking from here onwards. We are assigning A is equal to 0, B is equal to, C is equal to 1. After 10 nanosecond again we are applying 110, next I am applying 001, next 101, and here is 010. So total 4 test vectors we are applying, test vectors, and finally we are ending the process. These things are repeated. So like this, as given the mention, 4 input test vectors we are applied and the process.